three outer circles in this diagram. Which outer circles? These ones here. 1, 2, and 3. So these three outer circles are equally spaced on the circle in the middle. And here is your circle in the middle, number 4. Each of the 4 circles shown have a diameter of 10 meters. Find the area of the 3 regions that are common to 3 of the 4 circles. The 3 regions that are common to 3 of the 4 circles are these leaf-shaped regions over here. So what we want to do is we want to find the sum of these 3 leaf-shaped regions. There's of course more than one way to solve this problem. One of the ways that this problem can be solved is this. Let's make this diagram bigger, and we are going to begin with labeling it. Let's call this left one as number 1, right one number 2, bottom one number 3, and the one in the middle, this is number 4. So what we are going to do is we are going to use some geometry and a little bit of trigonometry to solve this problem. First thing that we're going to do is we are going to locate the center of circle number 2. Now, instead of circle number 2, we could have used circle number 1 or 3. All that we care about is that we are choosing the center of an outer circle. It's just a matter of choice that I'm going with circle number 2. We know that the center of circle number 2, it is going to lie somewhere on this circle. So we're kind of estimating here that this point, this is the center of the circle number 2. Next thing that we're going to do is we're going to draw 2 straight lines originating from the center of circle 2. One line will go to the center of circle number 4 here. So this line, this is basically the radius of circle 4 as well as the radius of circle number 2. The second line, that is going to go from the center of circle 2 to this point over here, where circles 2, 3, and 4, all 3 of them are intersecting. Let's now go ahead and label these points. Center of circle 2, let's call that as O. And this point at the center of the whole diagram is A. And this other point where circle 2, 4, and 3, they are intersecting here. That is point B. Next thing that we're going to do is we're going to connect point A and point B. This gives us a triangle, OAB. What kind of triangle is it? This is actually a special kind of triangle called as equilateral triangle. How do we know that this is an equilateral triangle? Easy. As you can see, OA, which is this over here, and OB. These are both radii of circle number 2. And as you can see, AB and AO, they are also the radii of circle number 4. And since all these 4 circles are identical, all these have identical diameter, that means their radii are also identical. So this triangle, AOB, it is an equilateral triangle where each of the 3 sides is equal to 5 meters. Let's write it down. OA equals OB equals AB equals 5 meters. All right. So where do we go from here? What we are going to do is, if we could find the area of this pie-shaped region of circle number 2, this sector over here, and from there, if we subtract the area of this equilateral triangle OAB, what are we left with? We're left with this half of a leaf. So once we have the area of half a leaf, from there we can find the area of this whole leaf. Once we have the area of one leaf, can we find the area of 3 leaves? Sure can. And that is exactly what we are going to do. Now that we know the concept of how we are going to do it, let's jump into the numbers. All right, let's make some room here. So here's what we're saying. We're saying that area of half a leaf is equal to area of the sector. Which sector? That is bound by points O, A, and B. Minus. From this, we are going to subtract. What? We're going to subtract area of the equilateral triangle OAB. All right, so this is the concept that we're going to use. Let's go ahead and find the area of the sector that is bound by point OAB, and that is this pie-shaped region. All right, so to solve for the area of the sector, we're going to make use of the fact that this angle over here, which angle? This angle is 60 degrees. Well, each of the internal angles of an equilateral triangle, they are 60 degrees. So 60 degrees, this is 1/6 of 360 degrees. Why are we talking about 360 degrees? Because we know that to go around the circle, we travel an angle of 360 degrees. So 60 degrees is 1/6 of the 360 degrees. 360 degrees is the angle to travel the whole circle. So 60 degrees, it is 1/6 of 360 degrees. For 360 degrees, we have one complete circle. So basically, the area of this sector here, it is 1/6 of the area of the whole circle. So here we go. Area of the sector is 1/6 of the area of the circle. Let's go ahead and calculate that. Area of the sector bound by OAB is equal to what? It is equal to 1/6 times pi r squared. 1/6 times pi, r is 5, square it. So what do we get here? 25 pi. All right, let's make it a bit smaller. Over 6 meter square. Why this meter square? Because we have this 5 squared, and each of the 5 is actually a 5 meter. So yeah, we can put it here too. So 25 pi over 6 meters square. Let's just leave it in this format for now. We're now going to figure out the area of this equilateral triangle OAB. To find the area of this equilateral triangle OAB, that we need to subtract from this area of this pie-shaped region. We need to figure out the height of this triangle. Which height? This height over here. How do we figure out this height? Let's do one thing. Let's redraw this triangle over here. I don't know if this is exactly an equilateral triangle, but we're going to call it as an equilateral triangle. Which one? OAB. We know that each of these angles is 60 degrees. To find the area of this triangle, OAB. What do we need to do? We need to do 1/2 times AB times, we're going to draw this height over here. Let's call this point as D, times OD. Now, AB, we know AB is equal to 5 meters, but we do not know OD. Can we figure out OD though? Yes, we can. How? For that, we are going to use this triangle OAD. What kind of triangle is it? This is a right-angled triangle. For a right-angled triangle, we can use basic trigonometry to find the height OD. So we know that sine of 60 degrees for triangle OAD, or we could have used the triangle OBD, doesn't matter. This is equal to the opposite OD divided by the hypotenuse OA. From here, OD is equal to OA sine 60 degrees. All right, let's scoot it up. OA is 5 meters and sine of 60 degrees. This is square root of 3 divided by 2. So here we go. OD is 5 square root of 3 divided by 2 meters. This is our OD. We come back to now the area of the triangle OAB. So let's go ahead and substitute the value of the AB and OD. All right. So what do we get? We get 1/2 times 5 meters times 5 square root of 3 divided by 2 meters. What do we get? We get 25 times square root of 3 divided by 4 meters square. All right, so here we go. Now we have area of the sector, which is 25 pi over 6 meters square, and the area of the triangle, 25 square root of 3 divided by 4 meters square. Let's now figure out the area of half a leaf. Here we go. Area of the sector, that is equal to 25 pi divided by 6 meters square minus, what is the area of the equilateral triangle? It is 25 square root of 3 over 4. 25 square root of 3 divided by 4. Let's put this inside the parentheses, meter square. All right, so this gives us, I'm going to scoot this a bit up over here, and I'm going to put a line here. Now what we can do is we can factor out this 25 from the numerator, and from the denominator we can factor out 2. Let's go ahead and do that. 25 over 2. Inside the parentheses we are left with pi divided by 3 minus, we have square root of 3 divided by 2. Parentheses closed, meter square. 25 divided by 2. Inside the parentheses, I'm using a calculator here. What do we have? We have pi over 3. We have pi over 3 minus square root of 3 over 2. Putting this in the calculator, we get 0.1812 meters square. Multiplying this by 25 and dividing by 2, 2.26 meters square. All right, now that we have area of half a leaf, which is this over here, can we figure out the area of 3 leaves from here? Sure can. How? multiply this by 6. Let's go ahead and do that. So here we go. We want to find out the area of 3 leaves. That would be equal to 6 times the area of half a leaf. What do we get? 6 times 2.26 meters square. That gives us 13.56 meters square. If you want, you could round it up to 14 meters square. This is your answer. So here you go. Problem solved. This kind of problems are not only important if you are preparing for math competition exams, but they're also very important to improve your critical reasoning and logical thinking skills. I hope that you enjoyed this problem. Don't forget to like and subscribe so you don't miss on new problems which are going to keep coming on this channel. Thank you for watching.